So our next example is one that's very close to my heart. And it's also going to be our first example of a non-commutative group. So example 2 is the permutation group. And I'm going to write that as Sn. Sometimes it's also called the symmetric group, and I'm okay with that. So AKA the symmetric group. And as a set, so I have to give you a set and an operation, remember. So the set is all permutations from the set, well, 1 up to n to 1 up to n. And the operation, so a permutation is a function, remember. It's a bijection from 1 to n back to itself. So for example, if I have the numbers 1, 2, 3, 2, 3, so this will be an element of S3. One example of a permutation is something that sends, say, 1 to 3, 2 to 1, and 3 to 2. Okay, and I'm going to call this permutation sigma. This, by the way, is called the Braid notation. So that's the Braid notation for sigma. There's also what we can call the two-line notation. And the two-line notation, you just write the numbers 1 up to n, and then where they get sent by sigma. So 1 here goes to 3, 2 goes to 1, and 3 goes to 2. Maybe I'll give you another example at the same time. So 1, 2, 3, 1, 2, 3. So let's have another permutation here. I'm going to call it tau. And we're going to have, say, 2 go to 3, 3 go to 1, and 1 go to 2. Okay? So the two-line notation for this is I write 1, 2, 3, and then 1 goes to 2, 2 goes to 3, and 3 goes to 1. Now you'll notice that here we just wrote 1, 2, 3, and 1, 2, 3 for the first line. And in fact, for any permutation, that's going to be the same, and that gives rise to the one-line notation. And the one-line notation, you just omit the first line. So this one's 3, 1, 2, and this one is 2, 3, 1. Okay? All good. Now, by the way, a really somewhat more technical way of writing this is that this is sigma of 1, sigma of 2, dot, 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 up to sigma of n for the one-line notation. Because this is just where sigma sends 1, where sigma sends 2, where sigma sends n. This sigma sent 1 to 3, so we wrote sigma of 1 equals 3 there, and so on. Now, like I said, I've given you a set, and I've even given you a couple different ways of writing it down. Now I need to give you an operation. Operation is composition of functions. So composition of functions. So if I wanted to do sigma and then tau, I just connect the dots. Dot, 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 dot. And so now I see where 1 goes under sigma, goes to 3, and then I see where 3 goes under tau, which is to 1. So then Now this will be perhaps a little bit confusing, but tau of sigma of 1, because I apply sigma first and then tau, so sigma hits 1, and then tau does something to where sigma of 1 went. So that's 1 goes to 3, and 3 goes to 1. If I do tau of sigma of 2, then I get 2 goes to 1, and 1 goes to 2. And if I look at 3, 3 goes to 2, and then 2 goes to 3. So that means that tau of sigma in one-line notation is just 1, 2, 3. Okay? In fact, that's a very special permutation. If I look at 1, 2, 3, 1, 2, 3, and just draw a straight line straight across, so this is the permutation 1, 2, 3, right? So those guys are the same. Now if I put any other permutation after this one, something like that, say, then I get the same thing back, right? So if this is, say, kappa, then this permutation times kappa is just going to be kappa again, because 1 now goes to wherever kappa went, 2 goes to wherever kappa went, 3 goes to wherever kappa went, right? Likewise if I put it on the other side. So in fact, this permutation 1, 2, 3, and more generally 1 up to n, is the identity. So I said earlier that we should always check that our things that we're claiming to be groups are groups. This is the first property. We have an identity permutation. It's just the permutation 1 up to n. And we've sort of seen one example of an inverse already. Sigma times tau was equal to the identity. So tau and sigma are inverses. In fact, inverses will always exist because, if you think of what a permutation is, it just means switch some things around somehow, right? And you can switch them around however you want. So if I mix some things up, it's possible to unmix them, put them back in order. And that's why inverses will always exist. For the two-line notation, if you take the two-line notation and flip it over and then sort the elements again, so 3 goes to 1, 1 goes to 2, 2 goes to 3, 3 goes to 1, 1 goes to 2, 2 goes to 3, 3 goes to 1. That's another way to compute the inverse. That is maybe a little bit fast, but you can try it on your own. So inverses exist. For any permutation you want. Finally, we need to show that this is associative. And my favorite way to see this associative, there's a few different ways to do it. So I'll sort of show by example. So for associativity, I really need a product of 3 things, right? So let's suppose we have some permutation like this. I'm not going to bother drawing the gap this time. I'm just going to draw straight across. So this will be sigma, this will be tau, and this will be kappa. And then maybe we've got something like this, and then maybe we've got something like that. Okay? So then sigma tau kappa looks like it's 1, 2, 3. Oh, look, it's the identity. So sigma times tau times kappa is equal to the identity. That's interesting. Now, we need to check associativity, right? So I'm going to tell you how to check associativity. So that means we have to check sigma tau kappa is equal to sigma tau kappa. Our product with the Braid notation is just forgetting that the dots in the middle exist, and then maybe sort of straightening things out a little bit. So if I do sigma tau and then kappa, it means I forget about these dots for sigma tau, and then multiplying by kappa means I forget about these dots and just follow everything all the way across. On this side, Doing tau kappa means I forget about these dots. And then doing sigma means I forget about these dots. In fact, forgetting about the dots, it doesn't matter which order I do it in, I still have the same picture without dots at the end. Therefore, these two things have to be the same. And as a result, Sn is associative. All right. One last thing I want to do before we move on to one more example is talk about commutivity. So let's look at this tau and kappa. So we've got tau does this, kappa does this, that's tau, that's kappa, and then tau kappa in one line notation is 3, 1, 2. Yeah? On the other hand, if I do kappa then tau, so kappa looks like this, tau looks like this, so kappa tau is equal to 2, 3, 1. And those are not equal. Therefore, the symmetric group is not commutative. So this is our first example of a non-commutative group. Symmetric group's actually very, very important. And so it's one we're going to come back to quite a bit.